Okay, so this is a reference sheet. It's not part of your unit booklet. It's kind of something to keep beside you while you work through the rest of this unit because there is some key terminology that you're going to probably want to look back on, and also just some key principles that you're going to want to know about graphing quadratic functions. So first of all, we need to define what is quadratic. So this keyword right here means that we need to have a highest degree of 2. In our function. So our base or parent function is y equals x squared, or f of x equals x squared. Okay, that's as simple as we can possibly make a quadratic function. Just a variable squared gives us our output. So we're going to start by defining what that is. We're going to use our terminology to kind of describe that graph, and then you can use this whole page as a reference when you go to talk about any other quadratic functions. So what I'd like you to do to start is just by filling in this sheet, but we're going to start at -3 and go to +3. Okay, so if you're like, oh, how do I do this again? I'm a little rusty. Okay, all we do is we plug and chug. This is our input. And this is what we're going to get once we put it into the function and solve. This is our output. So our first one is going to be, well, y is x, or -3 squared, which would be +9. Okay, so pause the video right now and take a second to fill this in. So we get our values filled into our table by solving, by plugging in x and then squaring it, remembering that negatives become positives when they multiply by themselves. So what kind of things do you notice about this? You might notice some different kind of patterns in the values. We are going to put this on a graph just so that we can really kind of visualize what these numbers might look like. So the first thing that we have to do when we're making a graph is we need to choose our scale and we need to put it somewhere appropriate on our grid. So I only have positive y values, so it doesn't make sense that I would have a massive amount of space on my grid dedicated to negative values. I do, however, need kind of an even spacing for my positive and negative x values. So I'm going to put my y-axis right in the middle of my grid. Okay, so label it my y-axis. But my x-axis, I'm going to put way down near the bottom in order to allow for as much space for those positive y values, since I don't have any negative ones. And that's going to be my x-axis. So that's step 1, is just choosing where you're going to put your axes. Then you need to choose your scale. So horizontally, I've got lots of room and I only need to go up to 3. So I'm actually going to go up by 2 horizontally in this particular example. So 1, 2, 3, -1, -2, -3. Now, we need to go and use the same scale in both directions once we decide what we're going to do on any axes. So x, I chose to kind of go up by halves, or skip every second line to fill in my values. For my y values, I'm actually going to just go up by 1 because I need to go all the way up to 9. And if I skipped every second one, I would not be able to fit 9 in here, I don't think. No. 2, 6, yeah, definitely not going to fit 9 in if I follow the same scale. But my y-axis can have a different scale than my x-axis. That's totally allowed. So I am instead going to go up by 1 here. So 1, 2, 3, 4, 5, 7, 8, 9, 10, etc. Now, you don't actually need to label all of those. If you just went ahead and labeled 1, -1, and +1, that would totally be fine because you're still defining your scale. But it's always helpful to actually have all of the numbers written down. It just makes it a little bit quicker when we go to do all our actual plotting of points. So I'm going to keep them all there. From here, now I need to plot these actual values. So remember that when we see them written in a table of values, what it really means is like 1 and 1, 0 and 0, -1 and 1, -2 and 4. And we always write coordinate points as x, then y. Okay, always. There's never an exception. Horizontal before vertical, independent before dependent, input then output. Okay, whichever way you want to think about it. From here, I'm going to plot all these. So I've got 0 and 0, 1 and 1, -1 and 1, 2 and 4, 3 and 9. 4, -3, and +9. Okay, well, that is not a straight line. Okay, so first of all, do not start connecting it with straight lines. Okay, that is not how this works. This shape actually is a parabola, and if we solved for all the little values in between, we would find that it actually creates a curve. So what you see, I always struggle drawing these on our screen here. I'm gonna curve to connect the points, and it's gonna keep kind of becoming steeper and steeper. I'm gonna do the same over here. Okay, so that is my curve. Okay, please note it is not a V down here. It must be curved. Okay, so it's not coming to a point like this. Do not draw it like that at all. Okay, that is what we call a cusp. It's a whole different set of parameters that produce that kind of appearance on your graph. So we're always going to have this very curved bottom. So be very conscious when you're drawing them that it must be curved at the bottom, not a V like that. That is wrong. Okay, this shape is called a parabola, and every quadratic function makes a parabola on your graph. Okay, so whenever I start talking about parabolas, this is the shape that should come to mind. Okay, so great. We've got our parabola, we've got our data points, we've got our function. Excellent. Now what? Well, let's talk a little bit about it. What kind of information do we actually get out of all this? Well, the first thing that it always needs to be mentioned when we talk about a parabola and a quadratic function is its vertex. And a vertex is its minimum or maximum point. And once you get into grade 12 and into calculus, you may also hear it called the point of inflection. Okay, so, and point of inflection just means it goes from going down to going up, or from going up to going down if it were to look like that instead. Okay, we always define it as a set of coordinate points. And again, always x then y. So in our parent function, this vertex is right here. I'm going to label it in blue. Is at 0, 0. The axis of symmetry is exactly where, if you remember the word symmetry and what it means, it's where we can like put a mirror and it would look this, our graph would look the same on both sides. So I'm gonna sketch my axis of symmetry in. Now it happens to, in this case, travel right along my y-axis. And in general, how we talk about it is we give it a name because it is a line. So I have to full on name it. X equals 0. And that's my axis of symmetry. And I'm just going to abbreviate that to AOS. Okay. So again, the axis of symmetry is the line of reflection, and it always passes through my vertex, actually. Okay, so if it always passes through my vertex, then my x value of my vertex is actually always going to be my axis of symmetry. I'm just zooming in so I can maybe write a little smaller and fit everything in better. Okay, so in this case, x equals 0. It is always the same as x of your vertex. X-intercepts, and we've heard this before. X-intercepts are where your graph crosses the x-axis. Okay, now you're going to hear some other words for this. You may also hear them called roots or zeros. Okay, so just some other terminology to be aware of. In our example of our parent function touches the x-axis and then kind of goes back up. We still call that an x-intercept. It still comes in contact with the x-axis. This actually occurs at x equals 0 as well. So we're getting some pretty consistent numbers. You'll find that as you work through vertex form, this will vary quite a lot depending on the equation. Our y-intercept then, if x-intercept is where our graph touches the x-axis, is where our y-intercept is where the graph touches the y-axis. Okay, and you're only going to hear it called the y-intercept. We don't have any other special names for it. So unlike x-intercepts, which is also roots and zeros, the y-intercept is the y-intercept, and that's all there is to it. If I go back to my graph and I look and I say, okay, well, where does it cross my y-axis? Well, it crosses at y equals 0. The domain of a function is all the possible inputs that we can have that are allowed. So, all possible, you can call them inputs. You can call them x values. You can call them independent values. And in our particular case of quadratic equations, there's no reason that we can't put a number into this equation. I can put in 10, I can put in 1,000, I can put in half, and I am totally able to square them. You can try it on your calculator. There is no reason that any number can't go in here. That means that my domain, all my x values, well, they can be anything. So we have two ways of writing it, either set notation or interval notation. I personally will default to interval notation all the time. It's just personal preference. If you like set notation, that is equally awesome. Okay, so interval notation or set notation. Interval notation would say, well, my minimum, always start at the minimum, is negative infinity, and my maximum is positive infinity. I can go forever in either direction, or anything is allowed. Set notation, we use curly brackets, and we say, well, x can be any real number. So this little e is an element, it's part of. Element of is how we read it. And this R means all real numbers. So that includes non-repeating decimals, repeating decimals, fractions, whole numbers, negative numbers. Anything goes, as long as it's not a negative under a radical. Our range is kind of matching up with our y-intercept. It's all possible outputs. Or all possible y values, or dependent values. Okay. When I go back to my graph and even just my deciding of what my scale was going to be, I said that I didn't need to go below my x-axis because I had no negative y values. So that, in essence, we were already talking about the range without actually calling it that. So when I go to talk about the range, well, it doesn't go below 0, but it can be 0. So my minimum value is defined by a square bracket because it actually exists on my graph. So in this case, my minimum is 0. That's the very bottom, the very lowest y value that I can have. But it can keep going forever upwards because as I square numbers, they keep getting bigger. So it goes all the way up to positive infinity. So you'll notice in interval notation, if something is undefined, we use a round bracket. Okay, an undefined meaning that we can't actually represent it on the graph. Square brackets if it is defined. If it's a discrete point on my graph. So I use a square bracket here because I actually have a point. My vertex is at 0, whereas I can't get to negative infinity, or to positive infinity because it keeps going forever. In set notation, it becomes a little bit more complicated once we have restrictions. So we say that y is an element of the real numbers. Yeah, that's still true. But y has to be bigger than or equal to 0. So that's the other half of set notation. So that's why I personally default to interval notation, because interval notation makes the assumption that it's all real numbers. And then it just is a matter of stating, okay, which real numbers within that kind of parameter. So those are kind of our key things that we need to be able to identify for every quadratic function. So whether you're looking at it in vertex form, which is the next few lessons, or in general form, which is our last few lessons, you always want to be able to identify the vertex, axis of symmetry, x-intercepts, aka the roots or the zeros, the y-intercept, the domain, and the range. Okay, so you're going to get lots of practice on that.